Okay, well, we're on the home stretch, and first of all, I just want to take a little opportunity to thank everybody for taking time out of their busy schedule. This has been an incredibly informative and productive and provocative, although I hope it gets a little more provocative even now, time. And so, again, on behalf of the organizers, I would really like to thank everybody for participating. And I think this is, as I say, it will hopefully be a good product. And this last little bit is really important for ensuring that, John's taking careful notes, I guess. Different people are taking notes, you're taking notes. So what we're going to try and do now with the panel, which I'll call up to the front, if you guys want to come up now. What we're going to do is we've assembled a distinguished panel of who've been listening intently all along and are going to give us a summary of their thoughts and what they've heard over the last day and a half. And then what we will do is we will open it up for discussion, where we'll talk about sort of the path forward and what other people have heard in terms of their thinking. There's some things that we've thrown out that we've sort of admitted that we'd like to do differently maybe. What will be that path forward will play a key role in sort of the recommendations that ultimately go into the overview paper that John just described. So with that, we're going to start with Professor Ramanathan, who has his first slide up. And I think the other three will make verbal comments, and I'll introduce those as they come along. So.
Thanks, Kim. I first want to thank the organizers, Kim Prather, John Seinfeld, and Ian, for putting together an excellent conference. I learned a tremendous amount. At my age, that doesn't happen that often, so thank you. I really like the way how we started with Ken Carslard telling us about putting the framework of modeling uncertainties, and then we marched on from individual processes, and then today we heard the global context of all that. So I'm going to pick up on a couple of 2 or 3 major issues which came up, which is first, should we be observing or should we be modeling or should we be analyzing what we have? But I think one thing which came up was that what we really need to understand this problem is the ability to observe the atmosphere simultaneously at various levels. I think it was somebody brought it up. They said it's impossible for NASA to fly 2 aircraft at the same time. But fortunately now, a university graduate student can do that. So, and I'm just pointing out to you, this UAVs is developed in my lab, mainly by students and postdocs. And all I told them was, I'll give them a big truck of an instrument. When you reduce it to the size I can put on the palm of my hand, bring it to me, and then we'll fly it. So over a period of 8 years, I myself was amazed and surprised what sort of sophisticated measurements can be made with UAVs. So that's something I'd like to bring up to this community. And we have over 14 instruments squeezed into half a shoebox size. That's about the size we have. The one you see wingtip to wingtip is about 2.5 meters. And we're able to fly 3 of them simultaneously so that we can look at flux divergences. And then the middle aircraft going up and down, measuring black carbon, cloud size distribution, liquid water content, so we can relate at a pixel level. And the second thing I want to point out is that the whole cloud radiative effect, Aerosol-Cloud, is about albedo. No one has ever measured that albedo. We have all implicitly assumed all you need is optical depth, and the rest comes for free. And I worked with the Earth radiation budget experiment from start. It was very interesting. I was, as a postdoc, there were 3 engineers who built this instrument, Irvine, and they were afraid to talk about it, so they dragged me to justify this to Francis Brotherton, Chris's father. This was in '77, and that's how that experiment got started. But Irvine doesn't measure albedo. And from the measurement it makes, to finally, when I got the albedo, there was about 500,000 lines of Fortran code. Those days it was in Fortran. So it's really not true albedo measurement. So you want to measure albedo, you really have to fly it very close to the top of the cloud. This is Greg Roberts was the postdoc at that time. So it's showing those three panels. The bottom panel was the middle aircraft measuring cloud microphysics. And then in the middle aircraft, you can see how the bump goes up. But that was after smoothing. The true measurement is shown on the top. And we have done over 300 hours of these UAVs in the Pacific Ocean, in the Indian Ocean. We have seen every effect you talked about here. When aerosol comes in, number of cloud drops increases, drop size decreases. We have never been able to see a change in the albedo. So there's still some mysteries out there, what you have implicitly assumed. The other thing I want to point out is that there's a paper of Yan Feng, Joyce Benner's former student, came to my lab. So I said, can we see asymmetry in the cloud optical depth? The model was predicting all the GCMs. Northern hemisphere clouds would be a lot brighter than southern hemisphere. It's not in the data. We pulled out the cloud optical depths, and the southern hemisphere cloud optical depth embarrassingly close, mainly in the ocean, within 3%, same as the northern hemisphere albedo. The models were suggesting it should be difference like day and night. So I was listening yesterday to I think there were only one chemistry talk on the organics, and then Kim Prather's group has done work on the organics from the ocean. Phil Rash, is there something going on there, compensating mechanisms? So that's why I would not completely dismiss what Bjorn Stevens said. We are probably missing something in the natural aerosols. It's worth poking around a little bit more in the southern hemisphere. So those two I want to point out. The third is what came out very, very clear in series of talks yesterday and this morning. We are missing the first hook in our modeling, vertical velocities, right? I don't even know what vertical velocities you assume. But it's measurable. So we did with this UAVs. This was done by another postdoc, Rick Thomas. He came from Manchester, and he's back in the UK. And we put 100 hertz. Remember, to measure turbulence, you need to have frequency more than 20 hertz. So we measured turbulent fluxes at the surface and measured it right through. And I don't know who made this comment yesterday, the velocity is not going to change. What we found, as the black carbon increased, let me back up. We make these measurements in the Indian Ocean because there's a fantastic dynamic range. When the air comes from south of that Maldives, the aerosol concentration is 100 per cc. When it comes from the north, it's 5,000, so we have a fantastic dynamic range. And we found systematically the turbulent kinetic energy was decreasing with the increase in the black carbon. Of course, the boundary layer is warming. It was breaking from stratocube to cumulus. So certainly, I don't think we can assume the vertical velocity distribution is independent of the aerosol concentration, at least when there's black carbon. I just want to throw it out there. So it's not as a horrendous measurement as you would think. It's doable, particularly with these UAVs. For turbulent flux, you have to fly very close to the ocean. It's dangerous to do that with conventional aircraft. So I just want to point out to this community, UAVs, now I feel I should be able to earn the bonus point because I'm not in the UAV business anymore. So it's not selling my UAVs, but this is a platform we have created. It's a huge thing. It can be done at an individual department level. So certainly, I would think our paper is still not out there. Christina was my student. She was in this experiment, and so they're all writing it. The academy is keeping her busy. She's not. All right. Anyway, so this is another thing. I have a feeling, I do agree there's enormous amount of data, but what I think is that any new measurement we make, we need to bring the chemistry, the physics, and the dynamics together. And I strongly agree with what Graham said. This whole aerosol cloud problem is about water vapor balance. That's what we try to do. We measured the flux from the ground and measured the flux at the entrainment layer to see, can we explain the water budget? We couldn't, because we were still not measuring enough. But what I want to suggest is that somebody proposed the system measurement. It is not inconceivable. We can fly 9 of these aircraft. We did 3 with just one pilot. 9 of these aircraft covering a 20-kilometer box. And the middle ones will be profiling, the upper and the lower one. The upper one will be measuring the albedo, the lower one will be measuring the dimming of the surface. All of this is possible. And it's not hugely expensive either. Anyway, so that's on the vertical velocity part. I want to move on. I think this is again picking up on Graham's point and what Ram made eloquently. I don't think we can see this cloud aerosol interaction as independent of what it's doing to the moisture cycle or the atmospheric heating. You know, vertical velocity is so important to you. We measure directly black carbon is increasing the heating rate by 1 degree Kelvin per day. That immediately, in the tropics, the adjustment is by sinking. So the vertical motion compensation is at least 0.5 centimeter per day. So how can you ignore that? It's all happening on timescales of few hours to few weeks. So this is showing the aerosol forcing at the surface and the atmosphere. And remember, the top of the atmosphere forcing, the direct forcing could be close to 0, as Ram clearly pointed out. That doesn't mean that aerosol is not impacting. Its dimming at the surface is -2 to -4. That's about 3% of the global precipitation. Look at the CO2 forcing, it's only 1/3 of that. So it's not surprising to me what Ram showed when he puts the aerosol decrease in the rainfall can dominate over the CO2. Because to relate to the -2 to -4, the global average evaporation is about 85 watts per meter squared. So that's about 3 to 5% of the evaporation the system has to balance. So we cannot just stop at clouds. Clouds ultimately rain and increase the evaporation. So I think we need to figure out that coupling. The last point I want to make is, so this shows that coupling which Ram showed. Remember, on a global average, the radiative heating of the surface balances evaporation, and the evaporation ultimately goes into the atmosphere as latent heating, and that balances the water vapor radiative cooling. So you put black carbon, increases the atmospheric heating by 2 watts, the latent heating has to come down because those two are in tight balance with each other. The last point I want to make, the other thing, I would have liked to hear a little bit more chemistry talks. So I'm surprised with the co-chairs being Kim Prather and Seinfeld. They probably lean too much on the other side. I think one of the exciting issues coming up is this whole thing about, we thought it was black carbon and then organic carbon was cooling. That's a plume. I was living in a village 3 years ago. So that's on the sun is behind that smoke. I have pictures from behind the smoke. It's pure white because on the reflection you don't see it. That's why satellites can't see absorption. When you see the transmission, you see the brownish smoke. It's organics. And a series of work done in my group, Kim Prather's group, and then now CMU, Carnegie Mellon, it's clear in a smoke like this, the brown carbon absorption is almost 40%. The remaining 50 or 60 comes from black carbon. So when you factor this in the model, the organic effect goes from cooling to either no effect or warming. So there is a huge underestimation of the whole. So this is a new issue. And I think so far our finding is this is something the chemists can dispute, is the brown part of the organic carbon comes from water-insoluble organics, versus the white part of the white part of the organics comes from water-soluble. This is, I'm quoting Johan, our Swedish colleague's work. Gustafsson, sorry. The last point. Yeah. Before I got into this, long time ago, my PhD work was on Mars and Venus. So when I got into this, I was asking, why is the Earth's albedo 29%? I'm still asking that question for 40 years. And as Ram clearly pointed out, models tune it, okay? And it was a beautiful thing you can ask, but without the clouds, the Earth's albedo will be 14, and the clouds double it. And you can simply argue, because the cloud albedo is 50%, but Graham Feingold clearly showed when 100% cloud cover, the cloud albedo goes to 80%. So there's no reason for Earth to settle into 29%. And you ask, why is that important? If the albedo was 27, the Earth would be nearly ice-free. If it's 31%, it will be completely glaciated. So we have settled onto this fine value of 29, and that's coming from the aerosol-cloud interactions. So if our models are not tuned, we would know what are the degrees of freedom available. So I personally think we have beautiful theories for the geochemistry of CO2, right? Given the carbonate rocks, you can figure out the CO2. And if you tell me the temperature, I can figure out the water vapor concentration. But clouds, it's not obvious. And that's why I show planet Venus. You can say on average, the Earth will be 50%. This is what meteorologists said, what goes up has to come down, it'll be 50% dry. Look at Venus, 100% cloud cover. And Mars, nearly cloud-free. Thank you.